Now, remember at the beginning when I was trying to explain to you about what the least squares means? Here's a better example. This is residuals. For a pair of sample X and Y values, the residual is the difference between the observed value of Y and the Y value that is predicted by using the regression equation. These are the values that we've observed. We get our regression line. We plug in our predicted value, and we get X equals 8, Y equals 4. That would be this point. We want to measure this distance to the line. Here is my regression equation. Y hat is coming from the line. That's our predicted value. My actual value of Y is 4 from the table. This equals -5. The distance from this dot to this line is -5 as stated there. Now we can go through and do that for all of our values. The least square property, a straight line satisfies the least square property if the sum of the squares of the residuals is the smallest possible sum. For example, here I have these residuals, -5, 11, 7, and -13. If I were to square all these values and add them, everything would become a positive value. The sum of the squares of the residuals is the smallest sum possible. That's what I'm looking for when I make my regression line. A residual plot is a scatter plot of the X, Y values after each of the Y coordinate values have been replaced by the residual value Y minus Y hat, where Y hat denotes the predicted value of Y. That residual plot is a graph of the point X, comma, Y minus Y hat. Now we're going to make another graph. We have this new graph, and this axis here is X, and the y-axis is going to be Y minus Y hat. I'll show you how to do that as well. To construct a residual plot, draw a horizontal reference line through the residual values of 0, then plot the paired values of X, comma, Y minus Y hat. I'm going to bring back StatCrunch and go stat, regression, simple linear. We're going to do everything like we did before. And then in these different kinds of graphs, we're going to do our residuals versus X values. Here's my residual graph. Analyzing a residual plot, the residual plot should not have any obvious pattern. The residual plot should not become wider or thinner when viewed from left to right. The chocolate Nobel data are used to obtain the StatCrunch generated residual plot on the next slide. When the first sample X value of 4.5 is substituted into the equation, we get that Y hat is equal to 7.84. Put 4.5 in for X, multiply it by 2.49, and subtract 3.37. This is the value you will get. For the first X value of 4.5, the actual corresponding Y value is 5.5. The value of the residual is the observed value minus the predicted value, or 5.5 minus 7.84. Where did we get this 5.5? Let's look at our values. 4.5 was the chocolate we observed. Our actual Nobel data that we observed is 5.5. When I plug my 4.5 into this regression equation, I get 7.84. I subtract them, and I get the residual. How do I make it look like that? These little bars down here. If I want to change the x-axis, Maybe I wanted to go from 0 to 12. I look at my y values. My minimum on the graph is negative 20. I'm going from negative 20 to positive 20. My label is residuals. I want a horizontal line at 0. That way I can see what's above the line and what's below the line. Now it's starting to look almost identical. We can also change the title. You can do whatever you like. Here I put residuals. I can go to my x-axis, and instead of having a label of chocolate, I don't want a label at all. Now it's gone. Here we see 3 different residual plots. The leftmost residual plot suggests that the regression equation is a good model. There's no obvious pattern. It's not getting thinner or thicker as it goes. So this is a good model. The middle residual plot shows a distinct pattern. You can see it's going up, then it's going down, suggesting that the sample data do not follow a straight line pattern as required. This is not a good model. And the one all the way to the right, as we go from left to right, the lines are getting further and further apart, or it's becoming thicker, which suggests that the requirements of equal standard deviations is violated. If there was a standard deviation, it wouldn't cause this pattern where it's getting bigger and bigger as it gets further and further away. The one to the left is good. As you can see, there's no real obvious pattern. This has a pattern, and this has wider or thicker. That's not a good model.